Assalamu alaikum everyone. My name is Mutaba Mohsin. I'm here with my team member to cover the topic threads. We will talk about single vs multi-threaded processes, use and types of threads, multi-threading model, system calls for threads, and at last conclusion. Starting with the introduction of threads. What are threads? Thread is a flow of execution through the process code. It has its own program counter, system registers, and stack. Each thread belongs to exactly one process and no threads can exist outside the process. To be more clear, we will cover the difference between single-threaded processes and multi-threaded processes. Single-threaded processes are the ones that execute one instruction of the process at a time. They are very slow for resource-intensive tasks, whereas threads can execute multiple instructions of a single thread simultaneously, and they are fast and reliable. To be clear about the difference between threads and processors, we will see. Processors are heavyweight and resource intensive. Thread is lightweight and is taking less resources than process. In multiprocessing environment, each process executes the same code but has its own memory and resources, whereas that is opposite in threads. If one process is blocked, no other process can execute, unlike threads. But in process we need operating system for interaction such as switching, context switching, but in threads we does not need operating system, which is one of the advantages of threads. Where the other advantages of threads are they are efficient communication, responsive, resource sharing, simplified design, but every advantages comes with some disadvantages, which are they lack security, debugging, complexity, overhead, and scalability. Yet, despite of having such disadvantages, they are still used in operating system, web browsers, games, and database systems. We will talk about the types of threads. There are two types of threads: user level threads, kernel level threads. User level threads implement user level libraries, so thread switching does not need operating system to cause interrupt to the kernel. In fact, kernel does not know anything about the user level threads and manages them as if they are single threaded processes, which is advantages of ULT. They are easy to represent, manage, and can run on operating system. As we said, there are some disadvantages along the advantages, which are the lack coordination between threads and operating system and require non-blocking system calls. The other level threads, kernel level threads, it is a method the kernel knows about and manages the thread. No runtime system is needed in this case. Operating system provides system calls to create and manage this thread. Advantages of kernel level threads are they should use multiple threads for the same process on multiple processes. If one of the processes blocked, the kernel can schedule another process of the same another thread of the same process. The advantages of kernel level threads are they are slower than user level threads and require thread control block, and complexity increases in this type of threads. Further, we will talk about types of models, which will be explained by my team member Manur Hassan.
So there are three types of models which includes many to one and many to many model. We will discuss three of them one by one. So first of all, many to one model includes many user level thread to one kernel level thread. It allows the application to create any number of threads that can execute concurrently. In this implementation, all threads activity is restricted to user space. Additionally, only one thread can access the kernel at a time, so only one schedule entity is known to the operating system. However, the entire process will block if a thread makes a blocking system call. Also, because only one thread can access the kernel at a time, multiple threads are unable to run in parallel on multi-core systems. Here is an example for many-to-one model. The program includes the necessary header files for using pthreads and the standard library function. It defines a thread function that is executed by each thread printing its thread number. In the main function, an array thread arguments is populated with numbers from 0 to numthreads minus 1. Then a loop creates numthread using pthread create function, passing the address of each element in thread arg as argument. After creating the thread, the program waits for them to finish using pthread exit function. Each thread performs its designated work and then calls pthread exit to terminate. The next is one-to-one model, which includes one user-level thread to one kernel-level thread. It is among the earliest implementations of true multi-threading. In this implementation, each user-level thread created by the application is known to the kernel, and all threads can access the kernel at the same time. The only drawback to this model is that creating a user thread requires creating the corresponding kernel thread, and a large number of kernel threads may burden the performance of a system. Here is an example code for one-to-one model. It creates 4 threads and assigns each thread a unique identifier. Each thread executes a function, a thread func, which simply prints its thread number and then exits. The program uses the pthread create function to create the threads and assigns the thread number as an argument to each thread. After creating all the threads, the program uses the pthread join function to wait for each thread to finish before proceeding. This ensures that the main thread waits for all the other threads to complete. Finally, the program returns 0 to indicate successful execution. The third one is many-to-many model. It includes many user-level threads to many kernel-level thread. It avoids many of the limitations of the one-to-one model while extending multi-threading capabilities even further. The many-to-many model, also called two-level model, minimizes programming efforts while reducing the cost and weight of each thread. Although the many-to-many model appears to be the most flexible of the models discussed, in practice it is difficult to implement. In addition, with an increasing number of processing cores appearing on most systems, limiting the number of kernel threads has become less important. As a result, most operating systems now use the one-to-one model. This is an example code for many-to-many model. It also creates 4 threads and assigns a unique thread number to each. Each thread executes the threadfunc function, which prints a message indicating the thread number like the previous one. The pthread create function is used to create threads, passing the thread identifier, default attributes, the thread function, and the corresponding thread argument. The pthread join function is to wait for each thread to finish its execution before the program exits. Finally, the program is compiled with the pthread library and executed, resulting in the threads running in an arbitrary order as determined by the operating system. Moving forwards, there are various system calls for thread which are discussed here one by one. The first one is pthread create function that is used to create a new thread of execution within a program. This function takes 4 arguments. The next one is pthread join function that is used to wait for a thread to terminate and obtain its exit status. The function takes 2 arguments. First one is a variable that identifies the thread to join, and next is a pointer to a void pointer that will hold the exit status of the thread. The next is pthread exit function, as the name indicates that it is used to terminate the calling thread and return an exit status to any thread that joins with it using pthread join function. The function takes a single argument, which is a void pointer that is used to return an exit status to any thread. The next is pthread cancel function that is used to request the cancellation of a thread. It also takes a single argument, which is a variable that identifies the thread to cancel. The next is pthread mutex init, which is a function that is used to initialize a mutex object, which is a short form for mutual exclusion. The function takes 2 arguments, that is a pointer to a variable that will be initialized by the function and a pointer to a variable that specifies the mutex attributes. The next system calls are pthread mutex lock and pthread mutex unlock, which are used to lock or unlock a mutex object respectively. Both of these functions takes a single argument, that is a pointer to a variable that specifies the mutex to lock or unlock. Now let us see an example related to threads. Here is a program which creates 4 threads and runs 4 separate functions in each thread. The threads are created using the pthread create function, and the functions they run are threadfunc 1, 2, 3, and 4 respectively. Each function simply prints a message indicating that the thread is running and then exits using pthread exit function. After all threads are created, the main thread waits for all of them to finish using the pthread join function. This ensures that the main thread doesn't exit before the other threads have finished running. Now, to sum up the presentation, I would say that threads are an essential aspect of modern computing, providing a means for efficient concurrent programming within a single process. By enabling multiple tasks to be performed simultaneously, threads can improve system performance and responsiveness. While threads offer several advantages over processes, including reduced overhead and faster context switching, their management can be complex and challenging. Proper synchronization mechanisms are necessary to coordinate access to shared resources and prevent conflicts between threads. Overall, threads are a powerful tool for concurrent programming, but their effective use requires careful design and management to ensure correct behavior and optimal performance. So that's all from our side. Thank you.